Hello, today I'm talking to you about power series expansion for multivariable functions, which is a topic that really doesn't get much play in the typical, calculus textbook that has a few sections on multivariable topics at the back of it. But I think it would be a good thing for us to do in this class because, last year in the single variable class, kind of one of the things we culminated with was turning things into polynomials. And you saw that that could probably actually be a really useful thing to do, right? To calculate values of things like sine, cosine, e to the x, transcendental functions that don't really have a nice way of computing them. Used to, we had to look them up in tables. And then you start to wonder yourself, well, how does my calculator even compute, the value of cosine of 1? And you saw that it computed it using a polynomial. So just to kind of review what we know about this, starting off in the regular single variable calculus case, we had some function that we wanted to approximate, right? And we could use a tangent line. Okay, so we would come in and we would draw a tangent line. And then, for places very near the point of tangency, the place where we were centered around, which we'll be talking about today, values of x nearby that, or this tangent line, this red line, was a good approximator of the function. Okay, but you can see that you go really any distance at all away from the point of tangency, and it's not going to be a very good approximator. And so we said, well, what if we found a polynomial that had, because kind of the hallmark of this tangent line is that it had the same y value and it had the same slope. Well, what if it had kind of the same curvature? What if we set the second derivative to be equal to the second derivative of this thing? And then we found that there was, out there was probably some parabola that would best fit the thing. And, I think it would be too hard to figure out what that would be. It would look a little bit like that, I think. Okay. Same first derivative, same second derivative. Okay. And what else was I going to say? Oh, and then we extended that to higher order polynomials, right? We could find an nth degree polynomial just provided that the function in white had n derivatives that we could take. Okay, so that's pretty much going to be the same idea that we're going to be taking here. It's just that we don't have like the derivative. We're going to have partial derivatives that are going to need to match up. And, just kind of the result here was that we could approximate f with an nth degree Taylor polynomial. And that nth degree Taylor polynomial was given by the sum as k ran from 0 up to n of the kth derivative of f divided by k factorial. Okay, and we evaluated the derivative at the point of tangency, at the point that we were interested in centering around. So, I'll call that point A. And then there was times x minus a to the kth power. I think I said that was k factorial, but I didn't actually write the factorial. Okay, that was kind of our formula for a Taylor polynomial of degree n. And then we did a little bit more analysis, using some of the tools that we had built up on series to figure out, when this thing converged. And we could see that, there were times where it was going to converge to f as n went to infinity. But that's not really the discussion today. The result of this was that we got really nice formulas. We got nice formulas for how to compute sine, cosine, e to the x, 1 over 1 minus x, and I'll just write a couple of them for you. Like e to the x was equal to 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial, and so on. Okay? And the more of these terms that you add on, the closer you get to e to the x, was the conclusion that we came to in Cal BC. For sine and cosine, we had other nice ones. You may have seen that the ones for sine and cosine and e to the x were so similar that there must be some sort of formula that relates all three of them. And there is, and I will show you that later in this course. It's really something that's, I could show you right now, but it's not the topic of this video. Okay, e to the x was this, maybe something like, I'll write down cosine x was 1 minus x squared over 2 factorial, x to 4 factorial. This one alternated because of the way that the derivatives of sine and cosine end up alternating in sine. Minus x to the 6 over 6 factorial, and you see the pattern. And again, the more of these that we added, the closer that we got to cosine of x. And then we got 1 over 1 minus x. And that one was really nice. That was 1 plus x squared plus x to the third and x to the fourth, and so on. And this formula was valid provided that x was between -1 and 1. Okay, that did not work when x was either 1 or -1. Right? Okay. What was I going to say? Then we realized that because polynomials are so easy to work with, we could manipulate these things and generate Taylor polynomials for other functions. Like we could generate a Taylor polynomial for arctangent by changing x to -x squared, just substituting -x squared on all these, and then anti-differentiating, because we know that arctangent is the antiderivative of 1 over 1 minus x, or 1 plus x squared, excuse me, which we could get by manipulating on 1 over 1 minus x. Okay, we did that, and then we also saw that certain troublesome functions like cosine of x squared, or e to the -x to the third, or something like that, that don't have closed form antiderivatives, we could write down an antiderivative for those functions just by, kind of composing on these things, and then anti-differentiating, and we ended up with nice polynomial representations of these, antiderivatives that we don't really have a name for. Okay, so that was what we used this for. This was really good. Okay, now we might be interested in cooking up some kind of a polynomial expression for a two-variable function. And the kind of the last thing I wanted to say about these was that the hallmark of these was that, f was equal to t at the point of tangency, or the point of centering. F prime was equal to t prime, f double prime was equal to t double prime. The nth derivative of f was equal to the nth derivative of t at the centering point. We just had all these derivatives existing and agreeing. So that's what we're going to need for the two-variable case. And now before I jump in, I'm going to tell you that the formulas for this, it's going to have more terms. And it's going to be pretty unpleasant. I'm only going to even go to degree 2. But you could see how you could go to degree 3 or higher. It would just involve a whole lot of terms, and I'd have to zoom way out and write big, and we don't want to do that. So, okay, I think I'm going to erase a little bit and jump in on two variables. Now, for two variables, the idea is that we're going to want all the partial derivatives to match up at the centering point. Okay, so the idea is, we're going to need some function f to be have enough derivatives. For the one I'm going to do, I only need the continuous second order partials. But say we're trying to cook up an nth order Taylor polynomial for a multivariable function that took in x and y, we would need f to be class Cn. Okay, which means it's n times differentiable and those derivatives are continuous. Okay, we need f to be Cn, hoping to find polynomial t with matching derivatives with f. Okay, so I want something like df dx equals dt dx. I want f x y y if I'm going to go up to 3 orders. The partial derivative of f, the third order partial with respect to x first and then y twice. I'm going to need that to be the same as what I would get if I did the same thing to my polynomial. And so on. We need all of these derivatives to match and to exist, that's Cn, and then match. Okay. So I'm going to start with degree 1. Okay, and and all of these being at the point A that I'm thinking. So for ease, I'm going to actually also erase the formula for the Taylor polynomial in one variable. It's going to be very similar, but I'm not going to actually close it down into collapse it into series notation because I don't think it would actually give you any more enlightenment as to what we're doing. So I'm going to go over here and I'm going to say for degree 1, we'll start with degree 1. So we're just going to need the first order partials. There's only 2 first order partials we can take. We can take the first order partial with respect to x and with respect to y. Okay, so for degree 1, I'm going to need t equals Let me think. Trying to decide if I should just give it to you and say, here, see it works, and I think that's what I'm going to do. It's going to be f of a, and by a, I mean a vector that's in the plane, and so maybe I'll call it ax and ay. Okay, so this is for f of x and y centered at the point A, which is going to have an x coordinate and a y coordinate. Okay, so t is going to be f of ax and ay plus fx evaluated at that times x minus ax plus fy times y minus ay. Okay, making sure I'm still in the shot. Yes, okay, so think about plugging in, think about plugging in ax and ay. T of ax and ay is going to be f of ax and ay plus 0 because we plugged in ax for x, okay, plus another 0 because we plugged in ay for y. Okay. If you take the first order partials of these things, you'll see that tx is just going to be fx because I only have one x here. Same with the first order partials there. But the thing that I really want you to notice is that this is actually, this is our tangent plane, right? Z minus z0 equals fx times x minus x0 plus fy times y minus y0. So I'm just going to say this is the equation of the tangent plane. But that should make sense, right? Because over here, our first order Taylor polynomial was the tangent line. Okay, and the tangent plane is essentially the same as the tangent line, just in the higher order case. Okay, so now I'm going to jump into degree 2. Okay, and so I'm going to take I think a more organic approach here. I'm going to say, okay, I know that it's going to be a polynomial, but that's really all I know. So I'm going to give myself plenty of room. Second order Taylor polynomial, which is going to take in x and y, is going to be, okay, I'm going to start with f. Oh, wait, no, hold on, pardon me. It's going to be some constant term. I'm going to actually fill in these pieces by matching up the values of f and t and f's derivatives and t's derivatives, and make sure that we all agree on what these actual constants need to be. It's going to be some constant plus some other constant times x minus ax. Some third constant times y minus ay. I think if I was going to do an example for you, I would presume that ax and ay were both 0 just to kind of like really compact this, right? Because it would be nice if we could just say, and maybe I'll do this in yellow off to the side. Let me just quick grab a piece of chalk. It's going to kind of be like c1 plus c2x plus c3y plus c4xy, c5x squared, and c6y squared. Those are like the things we're going for, but the problem is that we're centered at some ax, ay, and so we're going to need to account for that. And I don't want to just give you the kind of the Maclaurin series equivalent for two variables. I just want to give it to you in general. So plus C2, plus C3, plus C4. This will be the kind of the mixed one, x minus ax, y minus ay. C5, x minus ax squared. How much room do I have in my shot? Not enough. Let's see, maybe I can just zoom out a little bit or rotate the, that'll work for now. Plus C6 times y minus ay squared. Okay, that is a big polynomial, and that's only the second order polynomial, right? Like, we only have 2 powers. So you can imagine how many terms would be in, say, a fourth or fifth degree Taylor expansion. That would just be, it would be too many for me to write out for you and be making any sense along the way. So what I need is, I want to think about what's going to happen when I plug in ax and ay. Well, I need that to equal f of ax and ay, right? So it's going to be, when I plug in here ax for x, I'll get 0. I plug in ay for y, I'll get 0. All of these things are going to have zeros on them, so I'll just have c1. And so I know that that needs to be equal to f of ax and ay. Okay, and I think moving forward, I will probably just be abbreviating ax and ay with that, vector a. All right, but I also need to be able to take the first order partial with respect to x and have it equal the first order partial of f with respect to x. So what I'm going to do is I'm going to just say, and I'm also going to just be like abbreviating T2 is just T for now. Tx is going to be, when I take the derivative of this thing with respect to x, the derivative of a number is 0. The derivative of this thing with respect to x will be C2. Then the derivative of this thing with respect to x will be 0 because there's no x's in it. It's just got y's. We think that is a constant with respect to x. Okay, over here I'll have C4 times y minus ay. And, okay, 2 times C5 times x minus ax to the first. Okay. So when I plug in a to tx, I'm going to get, I'm going to plug in ax for x and ay for y, so I'll have 0, another 0 here, so I'll just have C2. In the exact same way, you would find that, pardon me, and I need the partial with respect to x of t to equal the partial with respect to x of f. Okay, and in the same way, you'll find the same thing with the first order partial with respect to y. So I'm going to say also ty at a, if we carried out that whole calculation, would be equal to C3, and that's going to be equal to the partial of f with respect to y evaluated at a. All right. Okay, for the mixed order partial, and I'm going to actually kind of remove my commentary of what we are needing and hoping. All right, so now for the second order partials, I'm going to need to be considering the txy. Maybe I'll do the mixed one over here. Maybe I'll be able to fit it. We'll see. Txy is going to be equal to, well, the derivative of this thing with respect to y, right? Okay, if I take the derivative of this with respect to y, I'll have 0, C4, and 0. Now I need that to be equal to the derivative of f with respect to x and then with respect to y. So I'll just say that's fxy at a. Okay, because we need these to agree at a, is why I'm just really emphasizing at a. Okay, now that means that I've got enough of these that I think I'm going to actually start filling in on my skeleton. So maybe I'll use orange in this case. We'll see. I don't think I've ever used this particular orange before. I'm not sure if it'll show up, but okay, C1, that's f of a. Plus C2 is the partial of f with respect to x at the point A. Yeah, it showed up. Okay, C3 was representing the partial of f with respect to y at A. Okay, and then C4 we found was the mixed partial. Okay, so that's fxy evaluated at A. Just showed that over here. Okay. Now, for the actual, like, you know, the normal second partials, I guess I'll start with txx because I haven't taken ty yet. I think you'll find that ty is pretty easy to take, but okay, so txx is going to be, all right, and then I'm going to want to be plugging in a. I didn't write it the last time, but I probably should have. If I take the derivative of this thing with respect to x, I'm going to have two c5s. All right, and then I need that to be the same as the partial of f with respect to x both times at point A. All right, so that means to me that C5 needs to be equal to half of fxx at A. Okay, and that's kind of where the factorial numbers are going to start to come in, and that was how we got them in the AP Calculus class. I was just, I think I did them in the context of, say, cosine or something like that, just to make sure that, you know, I didn't lose people in the f's and the x's and the a's. So C5 was going to be fxx divided by 2 factorial. And then I think that you would see, you know, I think maybe this is an exercise I'll leave for you, to find that C6 is going to be fyy divided by 2 factorial. Of course, evaluated at A. I just didn't leave enough room for me to fit all this stuff in here. And so here's we have a second order Taylor polynomial for a function f that is at least twice differentiable. Okay, if I was to go up to the third order, I feel like I kind of want to, yeah, I think I am. Maybe I'll pause this, erase some things, and kind of do some work on this polynomial that's got the orange things on it. So I can kind of show you a way that you could extend this to higher orders without having to run through this whole rigmarole the whole time. All right, so I rewrote this in a way that I kind of wanted to point out. Okay, so we've got, you know, kind of like we expect, f of a plus, okay, kind of the partials with respect to x and y. And then 1 over 2 factorial. If we factor it out like this, one thing I wanted to point out is that you will get, you know, 1, 2, 1. And 1, 2, 1, you know, I mean, that can happen just by chance. But this one is not by chance. This is kind of these are the binomial coefficient numbers. And so if we were to kind of condense this down and try to, you know, get an explicit formula for, you know, a given term, that we could use that. So what would happen is for the third order terms, if I was to have 3 orders of partial derivatives and I wanted to make a third degree Taylor polynomial for this thing, I would have 1 over 3 factorial, and it would be 1, 3, 3, 1. So it would be 1 of the third derivative with respect to x all 3 times, 3 of, what would that be, respect to x once and y twice, 3 of with respect to y once and x twice, and then 1 of y all 3 times. That's how this would generalize to higher orders, but as you can see, it gets pretty unpleasant. And kind of the big point I want to make here to wrap this up is that think back to what I was saying we would use this nice Taylor polynomial for in the single variable case, you know, to get values of cosine of x and e to the x and stuff like that. That seems to be a much more common issue, like to find the cosine of one number, than to say find the cosine of x times y, find the cosine of the product of 2 numbers. It's just not as frequent of a thing for us to need to do. And moreover, I just don't think that there's going to be as many nice patterns in the successive derivatives, successive partial derivatives of a multivariable function that there were in the single variable case, like, you know, e to the x with its own derivative every time, so it gave us really nice, a really nice Taylor series. The derivatives of sine and cosine, they kind of like, they cycled, which gave us a really nice Taylor series. I just think that's far less likely for this case. But it's something that's at y'all's level. You could definitely understand it. And I feel like it would be, good to include in my multivariable